and then we will start the activities. Please, Professor.
Thank you. Good morning. There is not too much to be added to what Liliana has already said. I am very happy to see, as she said, all these people here. This is the university. This is our normal way of working. So it's very nice to see that here. It's also very, very nice to have these distinguished invitees. And it's also very nice to have these invitees brought over Mexico by this young professor. By doing so, she is telling us that we can wait very many things from her. I'm very happy about that too. So please come, welcome to Mexico, welcome to the National University, and welcome to the Chemistry School. Thank you.
Thank you. Thank you.
Thank you. So please allow me to introduce to Professor Yu. I want to clarify that I will try to be brief because we can talk about his trajectory all day, but I will try to be brief. So Professor Yuntian T is a visiting fellow at the Hong Kong Institute for Advanced Study and chair professor at the Material Science and Engineering Department of the City University of Hong Kong in China. He is also founding editor-in-chief of the Materials Research Letters Journal since 2012. He was a distinguished professor at the North Carolina State University in USA. He was appointed as an adjunct professor and director at Nano Heterogeneous Materials Center of the Nanjing University of Science and Technology in China. Professor Yu has received his PhD degree in Material Science and Engineering from the University of Texas of Austin in 1994. He worked, posteriorly, he worked as a postdoc, staff member, a team leader at the Los Alamos National Laboratory until 2007. He received a lot of awards, including the TMS Distinguished Scientist Engineer Award, the ASM International Albert Sober Award, the TMS Leadership Award, and the SOMIA Award, among others. He was listed among highly cited researchers in the 2014 and 2016 by the Thomson Reuters. He has been elected in the 2022. He was elected as class of the Fellows of the National Academy of Inventors. His research focuses on the deformation mechanisms at the dislocation level and mechanical behavior of heterostructured materials. He also has interest in nano or ultra-fine grain materials. Professor Yu has a primary interest in fundamental aspects of the material science and designing materials with superior strength and utility. Professor Yu is currently among the 2% of the world's most cited researchers, and he's in the field of metallurgy. According to the metrics of Stanford University, and in Google Scholar, currently, Professor Yu has more than 55,800 citations. He's already over that. So we are really honored. And I just want to finish saying that we have the honor to have in front of us to the pioneer, the father of heterostructured materials. Please help me to welcome him to this talk.
Yes, thank you. That's a long introduction. Thanks. I'm really honored to come here to give you a seminar. I used to work at Los Alamos National Lab in New Mexico, so not far away from Mexico, but I never crossed the border. This is the first time I come to Mexico. That's to this university. Liliana went to City University of Hong Kong for less than 2 years. The reason when I saw her application to come to Hong Kong, I checked the university. Apparently, this is the best university in Mexico. So I was really surprised and very impressed. And I thought their students must be really, really good. So I was right, and Liliana was great, and she did so many things and very successful in the research. And today, I'd like to present this new field. We call it heterostructured materials. It's a very fast growing field. I'll show you more evidence why I said that. First, I'd like to introduce my collaborators. So the first collaborator is Professor Xiaolei Wu. Is his data, the first set of data, we could not explain with anything we learned from our textbook. That's what studied this new field. And later, so we worked on this with many collaborators. Here's my students from North Carolina State University. I joined the City University of Hong Kong in 2020. So I've been there for 3 years. Before coming here, I also thought about, our department in City University of Hong Kong. We are trying to recruit top students internationally. In Hong Kong, this university has the most international students. Since this university is a top university in Mexico, we'd like to recruit more students from you, PhD students, I mean. If you have, if you graduate from here with a bachelor degree, you want to do a PhD study, I think if you are top in your class, you pass the English exam, and I think it's very likely you'll get a scholarship there. It's not that hard because this is the top university from here, and then they give you very high marks. To motivate you more for some of the students, for professors, if you have top students in your class, please encourage them to apply to City University of Hong Kong for their PhD study. So our department, this is the ranking from last year, 2020. This year we don't know yet. Our department is ranked number 12 in nanoscience and nanotechnology globally. This is by the US News and the World Report. The material science department is ranked number 15. By the way, this is a very relatively new department. It's like it was formed like 7 years ago. And I was surprised myself with the high ranking here, but they hired many chair professors internationally, a lot of them from US and some from, a few from Europe. So if you find any students interested in doing a PhD study in Hong Kong, we will welcome you to apply. And so we have metallurgy, which is very strong, energy materials like a battery and the solar cell materials. And so, yeah, let me know if, according to your background, I can match you up with a professor there. But I cannot guarantee you to get the admission. But if you're top in the class, you have good English, you should have no problem. In Hong Kong, all the official business are conducted in English. The university, all the classes are taught in English. So I'm sorry, not many people speak Spanish there. I learned a few words in Los Alamos. I forgot most of them already. Sorry for that. Yeah. Yeah, heterostructure is not a new concept. It has been developed in nature over like of years. One example is this bamboo. It is bamboo. I don't know if you have bamboo here. I've not seen it yet. Assume you know what bamboo is. Bamboo is very tough and strong. In Hong Kong, this may be the only place in the world In Hong Kong, you see, when they make the scaffolding here, when they repair the building, all the scaffolding are made of bamboo. You'll be surprised how skillful they are in making the bamboo. See, my office is somewhere here. This is right outside of my office. And if you look at the bamboo, we look at the structure. So it's a soft matrix with strong fibers inside. In addition, the fiber distribution has a gradient structure. So this is the heterostructured. It's not a uniform structure. And so if you look at other examples, like human bones, you see this is has a gradient structure. And for seashells, it also has like a heterostructure. This like a calcium carbonate and with organic in between. That makes it strong and tough. In nature, why is it evolved for millions of years? Give you this structure because in nature we have like a strong storm or hurricane or something. The plants, the animals, they need to survive. They need to survive with the minimum material cost, which means they can grow fast and it's still strong. See, bamboo meets that criteria. And human beings also have been using this heterostructure for thousands of years. And one of them you might know this, like this in New Mexico, in the Pueblo, in Taos. All the buildings there are also in Santa Fe. They are made of this, they call it adobe house. Basically, in the old time, it's like a mud and straw. Right now, of course, they use the concrete and the fiberglass and glass fiber. And but in the old time, millions of years ago, that's what they used. And because that makes it tough. For more advanced technology, this is a sword like they found in AD 77 from Han Dynasty in China. They make the sword very sharp and tough. And then they wanted it sharp, but it could be brittle. You want to be sharp and also tough, so they got this into this layered structure. Composition has kind of this layered structure. That'll make it tough. And you look at others, like this samurai sword, it's also layered structure. This Damask steel sword, also layered structure. I think right now, there are still people trying to make this kind of artistic sword. This is the reason why they make it this way, because this makes it really hard and tough and strong. Of course, more modern, more advanced materials like aircraft, see, 787 Dreamliners, they use like a lot of composites there. Composites, I would call that heterostructure, but many people working on composites may be mad at me. So we call all those heterostructured materials. And I think a lot of my colleagues would be really upset. Say, well, I've been working there on this for like 50 years. Now you call that your material, you rename it. And so to make them happy, I'd like to narrow down this scope. The scope, so this is a definition of heterostructured materials. This is published in 2021 in this journal. This is a new journal. And by 14 professors working in this field. This is from like several countries. So we reached the consensus. We says this material got to have large mechanical or physical property difference. How much difference it is? Larger than 100%. Then you might ask, why 100%? Why not 99%? Why not 101%? Well, 100% sounds like a good number, right? As simple as that. So like nanomaterials, it's 100 nanometer, 100 nanometer. It's the same way. So this will make it easier to remember. If you have that, it does not guarantee to have great property. Okay? So we want only those material with a good property. We only want those. So we want to have another criterion, which is it has to have synergistic effect. I call this 1 plus 1 larger than 2 because if you have two components, you add their strengths together, you put them together, the overall strength should be higher than what you get from the rule of mixture. Got to be 1 plus 1 larger than 2. Got to have some extra good effect. And so where's the actual good effect from, the actual property from? It's caused by interzone coupling interaction. Or you can call that interzone interactive coupling. Basically, you have two zones with a very different property. You put them together, they got to affect each other. Across the zone boundary, there's an interaction. It's that interaction which gives you the actual property, what you cannot get with uniform structure. So this is not new either. If you think about it, think about the transistor. The transistor, right? You got this this PN junction, right? I mean, which one? And this is the P, that's N. You put them together, you got a transistor, you got a new device which has different property. So this is not new. This is not new. The only thing is, see, they made this. We never thought to use that concept to apply it to structural material like steels, like aluminum alloys. So now we're saying we use this kind of principle to apply to structural materials as well as other functional materials like magnetic materials. Okay? This interaction is different for different materials. For metals and alloys, the interaction is by dislocations. You think about it, you got one hard material, you got one soft material, you put them together, deform together. One is hard, one is soft, they have to deform together. They say, oh, how do we deform together? So they have to coordinate. How do they coordinate? They use dislocations. One type of dislocation is called geometrically necessary dislocations. What's these geometrically necessary dislocations? We call that GNDs. These GNDs, they are dislocations with the same Burgers vector. Okay? And we force them to deform together. They don't like it. They have to do it together. They will coordinate. They will generate this. This turned out to be really good for mechanical property. Okay? And for other materials, like magnetic materials, it could be by magnetic coupling. Okay? There's other functional materials, there's other type of coupling. When you have this coupling, you have this interface affected region, and that region gives you actual property. You add them together to give you superior property. So basically, that's what it is, although we don't know this before. So in this focus, since my area is structural material, so I will focus on metals and alloys because it's my area. And so for this, we need to have very large strength difference among different zones. You may ask, what is a zone? So it's not a grain. This is zone, we say, this zone, each zone can be polycrystalline or single crystal, which means it could be one grain, it could be a cluster of grains. So it's not a grain, it's a zone, like one area with different grain size, with different composition, or different phase. And we prefer all the zones can deform plastically. for conventional composites, usually one phase is brittle, like ceramics. I will tell you that that's not the best. That's not the best. With that, of course, this is the other one. We need to have 1 plus 1 larger than 2 effect. Using that definition, with what we learned already, there are several types of materials. We can call it heterostructured materials. One is called heterogeneous lamella structure. It's this type. This is what we found first, which gave us really great property. The second type, the layered structure. We see this layered structure wasn't new about that. That has been studied for like 30 years. But over the 30 years, they found a good property. They don't know why. Here, where I'm telling you why, what's the physics behind it. Gradient structure, so like a grain size gradient. You can also have a composition gradient. Like in industry, you have steels. You are, in the steel, they often like trying to diffuse carbon or nitrogen into it. That's composition gradient. It gives you similar property. And another code is seashell, bimodal, multi-phase. Yeah, all this are heterostructured. Then you might ask, if you look at this cartoon, they are so different. How can you classify them together? Here, we classify them together as heterostructure because their superior property comes from the same fundamental reason. There's a coupling via GNDs. Okay? This coupling via GNDs will produce strengthening and over hardening, which induces heterodeformation. And that heterodeformation gives you extra stress. That's what gives you superior property. Okay? So you can see this is very diverse. And depending on what you are working on, you can easily work on this. You can use ball milling, you can use ruling, you can use whatever you have in your laboratory. It's easy. Here I'd like to deliberate a little bit more on what's the typical heterostructures. One is called this heterostructured lamella structure. Basically, if you deform it, use cold ruling, and then you do a partial recrystallization, then you get this kind of cluster of large grains in a matrix of ultrafine grains. And so this size geometry, you can control it through your thermomechanical treatment. Another type is like a bimodal structure or trimodal structure. You have seen this in the literature. This is one famous paper, bimodal copper, published by Professor Emma. It has good ductility, high strength, and but I have to tell you that this is not the best structure to give you this good property. And gradient structure, you can do like this surface nanocrystallization, like a surface short pinning. A short pinning is an industrial process. And you can have this grain size difference. Surface is nanometer. In the center is coarse grain ones. Or you can use a dual phase structure. Like typically, see this is, if this is hard phase, that's a soft phase. This will be the hard phase in the soft matrix. If you look at our steels, most of our conventional steels, and also from our textbook, is mostly likely you have this hard phase in the soft matrix. We often say, this steel, this metal is not strong enough. We want to make it stronger. What do? We add reinforcement. The second phase, the hard particle to it. Like aluminum, like silicon carbide reinforced aluminum matrix composites. That's this concept. I will show you later that this is not the best way to go forward. This is like a 50%. Another type. If you have the softer phase inside the hard matrix, and the hard matrix can also deform plastically. This actually gives us the best property. But in our textbook, in the literature, we never thought about the design material this way. This actually is the best. Much stronger, much better ductility. This harmonic structure, this is by my friend Miyama in Japan. He published this, worked on this type of material for a long time. What he did was he got this like a large particle. He did like a low energy bonding. Surface of the particle is nanocrystalline. Inside is coarse grained ones. They consolidated them and formed this kind of a structure. He named it a harmonic structure. I asked him, what do you call the harmonic structure? It's like not easy to understand. He said he liked to play harmony in music. So this look like a periodic, like a musical note. So I think this might be easier to understand, but since he's the inventor, he is the right to name that one. And this is a story that when I told him, when he published this paper, I discussed with him, I said, this is the structure. He said, no, this is harmonic structure. The property is from, good property from textbook, like a list of like 6 to 7 reasons. I could not convince him. And later I sent his student to my lab for 3 months. I said, I asked the student to use his material. I said, why do you do a code ruling of this? According to our concept, that will give you much better property. So we did that. The property strength doubled and the ductility is still high, and he got convinced. So what I'm saying is, whenever you have a new material, new concept, most of the people, even the researchers, professors, their first reaction is, no, I don't like it. So it's really hard to convince the people. For the first few years, I was like arguing with everyone at a TMS meeting. Of course, now they don't argue with me anymore. Layered structure, this is the copper, brass, that's easy. And we use that one to study fundamental issues. So with this heterostructure, this is a new paradigm of materials design. And what's the theoretical basis? For this kind of structure, it can simultaneously increase the strength. When I say strength, I mean yield strength, not the so-called tensile strength or ultimate strength. And also the work hardening rate. This is important. Because from our textbook, you can find 5 or 6 mechanisms to make a material stronger. But most of these mechanisms will really reduce the work hardening rate. And to get high ductility, this is what you need. So this can give you both. So as a result, you get high strength and high ductility. For conventional strengthening mechanisms, so that's the problem. That gives you this so-called banana curve, which we can sometimes avoid use our heterostructure concept. Here, I've been talking about the principle is heterodeformation induced stress, which used to be called back stress, but we found it's wrong. We renamed it HDS stress. Now, where's that from? Actually, that's not that difficult to understand. If from our methodology textbook, when you have a front rate dislocation source, it immediate dislocations, they all get stopped by this zone boundary, this hard zone, soft zone. Of course, when we deform it together, soft zone will start deformation first. We'll start the front rate source first. Okay, assume the strength of the soft zone is 300 megapascal. If you apply the stress in 300 megapascal, these front radius source will start immediate dislocations. So if you apply the stress at 400, it immediate field dislocation, and then got all piled up here, and then this will stop operation because this all the dislocations has a repulsive force to prevent more dislocation emission, to prevent further dislocation emission or slip, which means it make this soft zone appear stronger. The strength might be 300 megapascal, but at 500, it will stop. If you want to emit more dislocations, you have to increase the load further. You got to like 800, get more dislocations, you stop it again. To make this one will appear much stronger. So that's, in this, what is called here, is called the back stress here, because it repels the dislocation to move forward. So always in a different direction of applied stress. Okay? On the other hand, and also look at our textbook, you have dislocation piling up at the piling up height, and here, you have a stress concentration. How much is the concentration? Is equal to N tau A. Tau A is the applied stress, what you applied externally. You have N in this as you multiply by N here. Okay? If you have this stress concentration pull up to put at the boundary, on the other hand, there must be another force to balance it. You know, for a force, you cannot apply a force to the air. And you have applied one force, 1 pound downward, so we get the anti-force going upward to balance it. So if you apply this on the other side of the boundary, it got to be a forward stress to balance this. At the boundary, it should be same as N tau A, but in the opposite direction. Since this is against the applied stress in the opposite, this must be in the same direction as the applied stress. That's what is called forward stress, because that makes the hard zone easier to deform. It makes the soft zone harder to deform. So you get the strength, here you decrease the strength. Well, at the interface, its magnitude for the stress and the back stress, they have the same magnitude, but opposite in direction. They cancel each other at the interface. If they cancel each other, that's not interesting, because when you do this mechanical testing, you cannot see any difference. They cancel each other internally. However, if you look at how this back stress decays, because of the dislocation distribution, it decays slowly. Here is a point stress, or it decays fast. Apparently, away from the interface, they cannot cancel each other. So those parts which are not cancelled, that give you, together, they give you the HDS stress. This stress, which means overall you have the extra stress to make the material stronger. They do not cancel each other totally. That's what we can measure from mechanical testing. So this is the principle, which is not that hard. I mean, this discipline piling up front radius source, that's all in our textbook. I would like to comment on that. When you do research, when you write your research paper, if you explain your experimental data, use your college textbook, for bachelor degree college textbook, that's called classical work. Okay? You have to dig really deep there to be able to use college textbook knowledge to explain your result. If it's too abstract and nobody understands it, it's like a really think about it, that's really deep, that means you do not understand it very well yourself. So this is not There's no mystery here, right? It's all from a textbook. Now, if you look at this more carefully, this is dislocating piling up. When in the metals, we say what's the plastic deformation from? It's by dislocating slip. Okay? Okay, your front reader source is here. Let's start from here. The front reader source is here. Okay? At this point, this dislocation never reached the interface, which means the plastic strength here is 0. Plastic strength is 0. At this point, the plastic strength is 1 box vector. At this point, the 2 box vector, because 2 dislocation past it. If you go all this, you smooth up your plastic strain as a function of distance from interface. It's like this. Okay? If you look at it, you derive it, the derivative as a function of the interface is positive. So you have a strain gradient. So if you have G and D pile up, you have a strain gradient. Okay? So they are all linked together. And you have G and D pile up, you have back stress, you have HDS stress, and you have a strain gradient. So this is called a positive strain gradient because the d epsilon dx is larger than 0. On the other hand, if your dislocation source is from the interface, it's opposite. The strain gradient is negative. We call that a negative strain gradient. So I'm saying that because this will be useful later. We talk about the G&Ds. Why do they call it G&Ds? Geometrically necessary dislocations, because when those dislocations act together, it causes the lattice strain, causes the lattice rotation. Okay? If all the dislocations pile up here, and you see there's half a plane for this, from all this so-called edge dislocation, and you can imagine this slip plane will bind. Will bind. It will bind to give you elastic strain. That's what's the back stress. However, if all the G&Ds pile up like this, from our textbook, you know that's a small angle grain boundary. For small angle grain boundary, and you get away from it, this stress field will cancel each other. So this does not produce strain hardening. Small angle grain boundary does not give you ideal hardening because away from it is this compressive stress, tensile stress. So alternatively, they will cancel each other. Okay? Of course, you also have this mixed type. From here, you would see to produce a strong back stress, to have a strong heterostructure effect, we want dislocation to pile up like this. Now from here, you would think, how do we make them to pile up like this? You think about the composition design, no cross slip, stacking for the energy, and all those can be used to design the alloy. Okay, this is another type of all the dislocations are like randomly tangled, of course, and it will make other dislocation hard to go across it, but it does not give you long range back stress either. In the long range, they cancel each other. Okay. So now you think about in the literature, and the metallurgy is not a new field. It has been there for over 100 years. And from our textbook, from literature, and for those many years, we never thought about using this back stress, HDS stress concept to explain the mechanical behavior. We seems okay. So what's the point of this? So for conventional wisdom, this is what they use. They call it Taylor's equation. So this is tau flow stress. So this is dislocation density for G&Ds in the statistical dislocations. So basically, it doesn't care what dislocation it is. It's only the total dislocation density. Okay? So this is a paper from Ashby, later by Hua Jiangao and Bill Nix in 1999. This paper got cited like 5,000 times. It's basically everybody is using it. Now, you can see here, the GND's density is together with that, the HDR stress is simply ignored. Ignored because for conventional materials, the effect from GND is relatively small. Our material science in metallurgy is not an exact science. So like people do hand waving, you know, it's okay. Explain my data very well, so what's the point? So that's okay. But as I will show you later, for heterostructure, that no longer works. It's not okay anymore. So heterostructured materials, let me summarize. I got a lot of this dislocation theory. I'm sorry for that. It's like very boring. Let me summarize this. I'll give you more interesting results later. You use HDR strengthening to improve yield strength. You use HDR work hardening to retain or even increase ductility. Okay? As a result, you produce a combination of strength and ductility that is not possible for conventional homogeneous material, which is what in our textbook. And so basically, the old principle of dislocation hardening still works. On top of that, we add another extra one to make things better. Okay? Some years ago, I was giving a talk at MS&T meeting in Pittsburgh. I said, everybody knows for metals, there's this banana curve. So like this coarse-grained material, it has high ductility, low strength. For nanomaterial, high strength, low ductility. So like you cannot have both. You only have one. You choose one. You choose this one or that one, or you choose compromise in between. So that's basically pretty much we know. And I said, how about I want both? I don't want to choose one. I want both. The whole audience, with 50 to 60 people, started laughing loudly in the audience. I said, well, you guys are laughing because you think that's a stupid question. So wait a minute, that's doable. Okay, then I'm presenting this. This is the first paper. We studied this new field. Okay, we studied with this titanium with a coarse-grained structure. The grain size about 43 micrometers. So after a symmetric ruling, the code ruling, you produce the ultra-fine grained structure. Then we know in the industry, when you do the ruling, next what do? Recrystallization. When you do recrystallization, you want to produce, if you look at the textbook, a uniform grained microstructure. Here, my colleague, Dr. Wu, he did the recrystallization at a relatively low temperature for a short time. He only recrystallized like 25%. Okay, got this structure. So this is like a recrystallized grains in a non-recrystallized matrix. If you look at the matrix, you cannot see the grain yet. Recrystallized region, large grains, free from dislocations. And so this is structure which gives us really surprising property. Okay, so this is for coarse-grained titanium. That's for ultra-fine-grained titanium. For heterostructured titanium, you got these data points. Okay, so the strength is similar to ultra-fine-grained titanium. The ductility is even higher than coarse-grained titanium. So we thought, well, this is great. We wrote a paper and we tried to publish it. At that point, I was working at North Carolina State University. We have Professor Bill Nix from Stanford visiting us to give a talk. At the lunch, I showed him the paper. I said, could you have a look at this? We found this really surprising result. I want to publish it. He had one look. He said, this does not make sense. What doesn't make sense? Firstly, you got 25% of the volume recrystallized, get a lot of grains. So the average grain size is larger. According to our textbook, according to the whole project relationship, your strength should come down. It's not coming down. So another thing is, when you did the recrystallization, the distal current density dramatically reduced. If you look at the Taylor's equation, that's distal current density. That should come down also. So it's violating the Taylor's equation. Another problem is, if you look at this strain hardening rate, which is the slope of the curve, this is the coarse grained ones, the ultrafine grained ones. You would think the heterostructured ones with a mixture of these two, it should be in between. But look here, it's even higher than coarse grained ones. So what's going on? So everything we learned from literature, from a textbook, none of them works anymore. Really cannot explain this data. So it took us like 2 more months try to explain what's happening. So at that time, we thought about the backstretch concept. I mean, this field is progress step by step. We don't know idea stress yet. And then Professor Nick said he agreed with that. So we published this in PNAS, Proceeding of National Academy of Science, in December 2015. Now that paper has been studied for over 1,000 times. So that explains why these strengths do not come down. You have to use this ideal stress concept. Otherwise, it doesn't work anymore. Doesn't work anymore. So in the future, when you do some experiment, you find some strange data. You cannot explain with any knowledge you learned. So the first thing to do is do the experiment and make sure your experiment is okay, your data is not wrong. If you're convinced your data is okay, then you might have a breakthrough in the theory. Okay? So now let's see why the strength doesn't come down. So we said this ideal stress, which is very abstract, hard to understand. But if we look at this is one large grain, about 4 micrometers. And look at this dislocation piling up. Each of these blue line has one dislocation piling up, the G and D piling up. You think about this. When you try to apply stress to it, this large grain will activate front rate source. The dislocation will try to pile up against this boundary. And however, it is surrounded by the harder matrix. The matrix is still elastic. It really cannot go across it, which means even when it cannot go across, and whatever plastic thing here, it does not register when you do the mechanical testing. You do not see the plastic deformation in mechanical testing, or you do not see enough to register. And so this started way before the yielding point. So it's until the point when this also started plastic deformation, then this grain can deform plastically. Otherwise, the shape is not going to change. Its plastic stress inside is not going to register. That's why that makes this grain, it should have a much lower strength. Because of this, it's almost as strong as the matrix. Okay? So that tells us, if you want to have a very high yield strength, you should design a material with the soft zone embedded in hard matrix. So that's exactly opposite to what we learned in our textbook. And if you see why you have this very high strain hardening, look at here. This sample was deformed to 9.4% strain. But those large grains initially is equiaxial. Now it's all elongated. If you calculate the aspect ratio, you calculate the average plastic strain there. So this plastic strain is like 45. Okay, total 9.5%, those are 45%. You can think about the hard matrix deformed much lower than 9.5%. So at the interface, if the interface is not fitting, you should have the same string, which means if this has the same string, this has much higher string, you got to have a string gradient. Remember what earlier I said, string gradient, GND padding up, back stress, forward stress, HDS stress, they are all linked. This tells you that it has actual HDS stress work hardening to give you that actual string hardening. That's why the string hardening rate is so high, higher even than coarse-grained titanium. Well, you cannot explain it. That's because of this. Like this. Okay, then you say, how do you measure it? We actually derive the equation to measure it. I'm not going to go to details. If you are interested, you can read that paper. And another thing is, this is another way to convince you, we measure HDS stress. Okay, for conventional material, this HDS stress should be like a very below that one, like here. So that's why we never thought about HDS stress before. We can explain our mechanical data very well because we don't need it. Its contribution is small. But here, in this material, this is much higher than that. We can no longer explain it. So that forces us to go to new theories, that develop new theories. So somehow when you have the data which cannot be explained, that might be a good thing. So we also use this concept to, on the gradient structured IF steel. For IF steel, the IF steel is used, developed in Japan for making cars. So this is already used in the car industry. Okay, so you want the steel to be strong, of course, so they can use less material to make it lightweight. Basically, one way to make it strong is to make a grain size small. So this is the strength. This is the ductility. As the grain size becomes smaller, it becomes stronger. The ductility will become lower and lower. Above 400%, the ductility reduces to like about 2%. For 2%, you will not use that one anymore. Ductility too low. And however, we use this gradient structure at like 600 megapascal, ductility is still about 10%. The strength, see, that's like 50% higher. If you use that one, use this one, you can significantly reduce the weight of the car. Especially for electrical cars, they're critical to, for the battery to run longer. And we also tried to slice each layer to measure the strength of each layer. When we add those layers together, it should follow the rule of mixture, the blue line. But when together, they follow this red line. So this is 1 plus 1 larger than 2. So together, because of their interaction, interactive coupling, it has extra strength there. In addition, when you deform it, the stress state at each zone also changes. So if this is hard, this is soft, initially you apply the uniform uniaxial stress, and if this one deform plastically first, it shrink more because this percent ratio should be 0.5 for plastic deformation. This should be 0.3. So you get from one uniform stress, you get into two-dimensional stress. That also gives you actual strengthening. So we found this when you have like this actual stress state difference, like you also get much better property. I'm not going to go to details there. So here, if you are convinced, say, I'm convinced, I want to work on this also. And how do I design a heterostructure? Now let's think about this. First, we say, what's the interaction from? Interaction at the interface, zone interface, right? So which means you want a high density of interfaces, okay? And how's the interaction? Is it G and D piling up? So which means you need to give enough space for G and D piling up. Too large, too small does not work. Too large is not effective. Too small, you don't leave enough space for G and D piling up. It's not good either. You do have an optimum spacing. So far, we found that optimum spacing is a few micrometers, below 10 micrometers. So when you design something, you can use that. Third thing is, contrary to what the textbook tells you, you want a soft zone embedded in harder matrix, not the opposite. Conventionally, we use hard zone, hard zone in the soft matrix, but now it's the opposite. So I said there's optimum spacing to get for the mechanical property. You look at, we use this one to verify that point. So this is a layered structure, and as the layer thickness, this is 125 micrometer, 64 micrometer. The layer thickness decreases initially. The ductility and the strength, they both will go up. And when it reaches the optimum spacing, continue to decrease. The spacing is from 15 to 7.5 to 3.7. If the strength continue to increase, the ductility started to decrease because you are not leaving enough spacing for G and D to pile up to give you this HDI strength hardening. So there's an optimum size when you do the design. Of course, we also verified the G and D gradient, and we also verified the strength gradient near the interface. Here's a story here. We earlier one said is a positive strength gradient and negative strength gradient. Positive strength gradient is when you have front radial source in the interior that goes pile up against the boundary. Negative strength gradient is when the dislocation sources are at the interface. Here we measure this negative strength gradient. So we came to a conclusion that the dislocation source are at the grain boundary, at the zone boundary in that paper. Later, we did experimental observation, and we found that, we found that is wrong because we found the dislocation source is still in the gradient, still inside the grains. And the only problem is all this dislocation from the source, they got generated, and when they got generated, they immediate field dislocations, and then they got disappeared, deactivated. And the dislocation source has a gradient. So what when you come to the conclusion, you really need to really see it. Sometimes your explanation is logically explains what you see, does not mean it's correct. So I'm not going to go to details here. If you are interested, you can go further. Sorry, this has been too long. I'm trying to finish it quickly. Another feature for heterostructure is we found that all the deformation are not uniform. They give you this string bands for all the gradient structure, all this heterostructure deformed in this string bands. That's not the case in homogeneous structured materials. We do not know why. So this is what we are trying to figure out for fundamental study. If you want to do some fundamental study, I encourage you to work on this. Okay. So I have finished all this boring scientific part. Now come to the end. For heterostructured materials, the biggest advantage is this. They can be processed with current industrial facilities. Like the first one is by code ruling. You can do that by code ruling, by powder methodology, by drawing. But all this industrial process, you only need to change the processing parameter. So that gives this type of material a life. If you have a new material which has no industrial application, it's not going to last very long. Now think about it, in the recent years, we have so many new materials from graphene, carbon nanotubes, high-energy alloys. How many of them really made it into the market? Not many. We just say we are wasting taxpayers' money without feeding back to the society. So this one, that's the best part. So that guaranteed has a long life. Secondly, since this is a new field, there are so many new material science we do not understand, we do not know, which is bad and good. The good thing, good for us, justify our proposal to get more funding, right? Because we want this funding. Why? Because it's new science, which is good. Also means if you are doing your PhD study after you graduate, there's still a hard field. There's a lot of unsolved problem for you to study. This concept also worked for functional materials. This is like a magnetic material. They want to use this hard magnet. They want high corrosivity, high magnetization. They had a trade-off also. Also, that trade-off is determined by this equation. This says there's nothing you can do. These two, they go opposite way. So they use this kind of concept. You got something here. So this is something that they have been working for like 20 years. They could not solve. It's this concept to solve this. Okay, if you are interested in this, you want to study, want to start to work in this field, I mean, I would recommend to read this paper first. And this is a recent paper published this year. It summarizes all this concept, processing, and everything. And for graduate student, if you want to teach your student, this has your textbook. It's just out. Now it's ready. It's on sale now. The publisher making money, not me. Okay. I'm sorry, it's also very expensive. For introduction to heterostructured materials, you go to elsevier.com. They have this active material series paper textbook. This is the first one in that series. Okay, you can go there to find that out. Okay. I said that this area is quickly becoming a hard area. My prediction is now hydrogen is very, very hard. But you know when is the hottest? What time is hottest in a day? Like 3 p.m., right? I think hydrogen is starting to cooling down. The next hot area will be this one. See, the conference is here. We need to do the first one every 2 years. Yes, this one. This in China annually. This in US every year. This one here, and of course this in Cancun, in Mexico. And so next week, this is also biannual. Then here easily, right? I'm not including workshops yet. There are several workshops in Japan, South Korea, in China every year. So these are all major conferences. Okay, and if you have good papers, publish here. This is I think for metallurgy, this is the best place to go. And our target is make it comparable to physical review letters. Of course, it's very, very tough to publish here. Thank you for your attention. I'm ready to answer your questions.
Thank you so much, Professor Yu, for this excellent conference. I'm sure that everybody learned a lot. I can see so many happy faces like, yes, this is new for me. So we are really happy for this talk. Thank you. Please raise your hand if you want to ask. You can ask in Spanish, and I can translate for you, or you can ask in English or in Chinese. So do you have some questions? Please raise a hand. Yeah, please, Eduardo.
Bueno, en español porque no quiero como complicarme la existencia. Menciona que debe de tener diferencia a lo largo del material en propiedades mecánicas y físicas, pero bueno, hubo más mención sobre propiedades mecánicas. ¿Es necesario que exista ambas forzosamente o solo con que se cumpla una basta?
Okay, Professor, I will translate the question for you. The question is that you mentioned in the talk that for heterostructured materials, it should be a combination of a synergistic effect of different properties, and you mentioned mainly mechanical, and you also mentioned physical. So the question is, if heterostructured materials should combine a gradient, means a big difference of mechanical and also physical properties, or is enough with only mechanical or only physical?
Well, I think you can make it both, depending on how you design it. Actually, my student, Ray Zhou, is working on this gradient material with both like a magnetic property and a mechanical properties. It's more complex to design it, but I think you can put them together.
Okay, thank you. Some other question, please raise your hand, Spanish or English or Chinese. Yeah, please, Charlie.
First of all, as someone who was a fan of his work before he knew it was his work, I'm very glad to meet you. And my question is, what's the next step for the heterostructural materials? I mean, in the industry and scientist investigation.
For the industry, are you saying for the industry?
Yeah, and scientist investigation.
I think it's really easy for industry. Right now, there are two big steel industries, companies, one in Shanghai, another in northern part of China. They are already working on making new series of heterostructured steels. And they saw our paper, and we used the ruling to make it a good property. They said that process actually maybe even cheaper than what they are working on now. So they are really trying to commercialize this. There are also some others like heterostructured titanium. There are a small company already formed to try to commercialize that. So this is really easy to commercialize because you don't need to buy new equipment, whatever you have. I mean, I saw you have the metallurgy lab here. And with those facilities, you can already make this kind of material. So that's easy.
Thanks.
Thank you. Do we have more questions? Please raise a hand. Yes, please, Sebastián. Can you, por favor?
Thank you very much. Thank you very much for your lecture. It was very illustrative. Well, I have a lot of questions, but let's start with one. Regarding the examples you gave about the dual phase material, this strange phenomenon where the matrix is the hard material and the core materials are the soft one. I'm really intrigued about that. I don't know if you could talk a little bit further of how was the deformation process and the microstructure afterwards? How do you explain this strange phenomenon?
Okay, then you have a cos grain, right? You have a cos grain. You know, each grain has a different orientation. When you do the deformation in the ruling, because of their different orientation, their plastic strain will be different. right? So some grain will store more dislocations, some less. When you choose a recrystallization temperature, in a short time, those has a higher dislocation density, they will recrystallize first. So when you see this one, like a lavender, like elongated with recrystalline grains, I think that's from one original bigger grain. So that's the trick for doing that partial recrystallization. You have to choose the right temperature, right time. So you have to try it. Okay?
Thank you very much.
But if you use a powder methodology, you can just add two different powders together. Control exactly what's
La pregunta es en español, que si alguno de estos materiales podría tener aplicaciones en el futuro para la industria espacial, y si sí, ¿como cuál?
Yes, Professor, I will translate the question. Is if the heterostructure materials have some future in aerospace applications? And if the answer is yes, if you can please mention some examples.
For aerospace applications?
Yeah.
Well, I mean, if you want to make it strong and tough, you can reduce the weight. I think what aerospace want. I mean, for every extra pound, every extra kilogram, it consumes a lot of energy to send it up. Especially for airplanes. I heard that in Canada, this airplane, they have a thick layer of paint to reduce the aircraft weight. They want to strip that off to paint it. So, so that extra weight is reduced means the airline can make extra profit. There was one funny story, like I heard some years ago, after 9/11, I think, the airline industry are losing money. So in Japan, this one Japanese airline asked all the passengers to try to go to the restroom before they board the airplane to reduce the weight. So
Okay, thank you. Do you have some more questions? Yeah, please, Professor.
Thank you very much for your presentation, Dr. Zhu. And congratulations first on creating a new area in material science, combined with new and old topics.
join us.
Yeah. And then I think one of the questions maybe still relate to the aerospace engineering, and then particularly for the high temperature alloys. For example, if you introduce such a kind of heterogeneous structure, you apply it at high temperature, any kind of, the extra concerns or maybe careful during the materials design we have to consider, because you showed a lot of cases with a probably lower temperature. Yeah.
Yeah, I think at a different temperature, you have different mechanism. At high temperature, this dislocation paragraph may not work anymore. But when you look at the silver alloy, do you know that it consists of two phases? Yeah, they got one hard phase, like a fiber, the other one is the matrix. So actually heterostructure, in my opinion. There's someone in CTU, he tried to see how this concept works for high temperature alloys. He found that heterostructure has a much higher fracture toughness. With the heterostructure, you got one phase with tougher there. But I'm not some like you got a fine grained one that doesn't work, of course. You have a different heterostructure.
Thank you. More questions? Please raise a hand. Yeah, okay. First here and then with Sebastian, okay?
First of all, thank you for being here, Professor. My question is, if I'm looking forward to do a master's degree in heterostructured materials, which are the top 3 universities or institutes to do it?
Oh, I didn't get your question. Yeah,
my question is, if I'm looking forward to do a master's degree, a graduate degree, which are the top universities to do it, related to heterostructured materials?
So you already got your master's degree.
Yeah, well, I mean, in 2 years that I come out.
Are you working for the industry or working at the university or?
Yes, I'm talking about the university for a master's degree. Graduate.
Okay, if you work on this area, I think this is at the point where the paper is easier to publish and you get higher citations.
Okay.
So I think this is a good time to start. When it really become very hard, when everybody is working on that already, and that's not, I mean, it's already too late.
Okay.
And now is a good time, I think.
Okay, thank you, Professor.
Thank you, me again. Sorry. Yes. I'm more curious about this example you made. My next question was about the dependency of the dislocation piling on the crystallographic plane, the crystallographic orientation of X-ray. Have there been studies you made in these cases to know if, well, first of all, which are the planes that are more, I don't know, desirable for the piling of this location, and even more if there's a global microcrystallographic texture on the material that could be more suitable for producing this location engineering problem of distributing in the direction or even the quantities of the dislocation piling up in a specific ways?
I don't get exactly your answer, your question. So you have, I think you have designed for more dislocating piling up. So that's a design. To do that, you think about when design, from alloy design, you want one of the alloy to have low stacking for the energy. Otherwise, dislocating will go cross slip easily. It does not like to pile up. So planar slip is desired. And then you want this interface in the heterostructure, how to design that. How do you process that in other quantity? I mean, in industrial scale. Of course, in your lab, you can just prove the concept. But the thing about industry, the best way to use industrial process to make them.
Okay. So if I understand correctly, it's more a mean of the stacking flow energy in the whole material more than a direction.
Material, yeah. So this is another thing, the question I often hear from people say, okay, for the customers, they always want to uniform material. You're telling us the heterostructure, they say no. What I'm saying is a heterostructure on what scale? Is at a micron scale. For the customers, what they see is a uniform material. So it's almost like on the highway, you see the highway is very flat, the freeway. But at a water scale, you look at it at a millimeter scale, it's not flat. Flat is not good at that scale, right? So overall, in a large scale is flat, but not at this scale. At a really micrometer scale, we do not want uniform structure. But for the customers, all they see is a uniform material for them to purchase.
Thank you.
Many people ask that question, so I have to answer this.
First, thanks for the presentation. My doubt is, what are the biggest challenges of heterostructured materials?
Oh, that's a good question. Good question often has no answer. So I think there are so many fundamental issues we do not understand. Ideally, you like to design the heterostructure before you make them. See what's the best. We're not there yet. So right now we want to understand, see that stream bands non-uniform deformation, what caused that, what's the reason at a dislocating level, we do not know. So Another thing is, when you deform it, it's like a software zone. When you deform first, it changes the stress state also. And this is particularly hard for material scientists to understand that, how that affects the mechanical property. We need people with the background of mechanics to do some modeling or whatever. So this really need people with different background to work together. Mechanics, computer modeling, experimentalists. Because this new area involves so many things. Like this HDS stress hardening, what we call. Actually, mechanics guy already found this phenomenon many years ago. They called it a kinematic hardening, like a phenomenological term they gave. For us, we want to give a physical definition. But they don't know the physics. We know the physics. We don't know how that affects property. So we really need a lot of people to work together. What I'm saying is, there are so many things to be studied. So, which is good for us too.
Thank you.
I hope more people will start working in this area. And this is the time to join, because this is the time which is easy to publish paper, to get funding, to get a higher citation, to make an impact.
Thank you. Last one, I promise. Well, is regarding the final example you gave about brass, these strange lines that form after deformation. Have you made closer studies of the, I don't know, even composition or defects present in these bands, and if they are?
You are talking about the string bands.
Yes, exactly.
We call this shear bands or local string bands, and we don't know. You know, we know this gene piling up. We don't know how this is related to that. But this is from digital image correlation. The width of this is in a micrometer range. This location is at a nano range, so we don't know how to link them up. We don't know how this is nucleated, how did it propagate. And you know, for nanomaterials, you have this one band, it will propagate through the whole sample. Here, it's more like you disperse them uniformly over this whole gate length, so that the whole sample will not fail. This kind of like a delocalization of the bands, like a dispersion, make it to accommodate larger plastic string. Inside the bands, there should be string gradient. There should be introduced extra string hardening. All those are questions we do not have answer. Right now, we have a project working on this with a neutron diffraction, and we are writing new proposals to study that. The funny thing is, when we write a proposal, we always have some idea. This might, some hypothesis, this might work. However, the breakthrough often comes when it's from somewhere you have not thought about. So you have to keep working on that. Hopefully, there will be a breakthrough coming from somewhere. So one day, it explains everything. So we're not there yet. I mean, this is the frontier of this field. I mean, fundamental frontier. We don't know. So we're trying to use like a institute, T, and digital image correlation and all this. It's not an easy problem.
Thank you very much.
You're welcome to work on that problem.
Yes, of course. Yes.
you. So if we don't have more questions, I would like to thank to Professor Yu again for this excellent talk.
Thanks.
And I will like to read this certificate of appreciation. I will read for you. Mechanical Engineering Department of the Chemistry College of the Universidad Nacional Autónoma de Mexico appreciates Professor Yuntian T for delivering the invited seminar, Heterostructured Materials, a Fast Emerging Field. Thank you so much, Professor. And I just want to point out that it's coming in a very beautiful case with the logo of the university and the name of Professor Yu. Please. And for last, I want to give a gift, a gift for Professor Yu, the official T-shirt of the Heterostructured Materials Group of Mexico. Please, Professor. So, thank you. We can please proceed. We have 30 minutes of the coffee break, and then we will continue with the talk of Professor Xiong about additive manufacturing. So we have 30 minutes. You can also use this opportunity to talk to professors. I'm sure that everybody will be very interested. Thank you. Professor, how are you? Do you feel okay?
I'm feeling okay.
You're not
Oh,
tired?
this big audience. I'm surprised. You have a
Even we
big audience
broke,
here.
we broke extra chairs and some people was outside.